Classical Physics Tutoring, Chapter 6, Section 2, Lorentz Transformation. Okay, so in the previous video, we talked about the coordinate transformation. And what it was is, say, this coordinate is, we have two coordinates, second coordinate moving at the speed v. Okay, so what happened is, say this car is on this coordinate and something on the dashboard, say glass of water, is there. Okay, and the person driving see glass of water is not moving at all, but from person sitting in the car and the car is not moving, and say, no, this glass of water is moving at the speed v. Okay, and two different observers claim two different things, and that's not issue in the Newton's law, because there is only one physics law allowed, which is based on absolute space and time, right? And physics law is created on this, and in this case car A is not moving, so this car A is kind of replacement of absolute space and time, and his physics law saying that the glass of water is moving at the v is the only physics law. And it doesn't matter what the driver and the car B observe, he need to accept that although glass is not moving in front of him, it's moving at v from the absolute space and time viewpoint. Okay, so this is the only reality we allowed. So sometimes you are sitting in a room and you don't know strange things going on. Suddenly you start floating or something happen, right? And it seems to be against the physics law. But if you find out your room or maybe car, the motion of your room against the absolute point in the space and time, then you can easily figure out why it's going, what's happening. Okay, because you are moving at the v and the glass of water moving at the v, so you don't feel glass is moving. So that's the correct interpretation of the physics law. But now we remove this in the, as explained in the previous video, the absolute time and the space. So we need to divide the world into two. The observer A in the car see the world one way. Observer B in the car B see the world different way. Okay, then do we have to create the two different physics? Actually, what we have to do is the conversion. Observer A can see how the observer B sees the world. Okay, the observer A, how observer A see how observer B see the world. The observer B sees the world by this coordinate system and time system, and the observer A can see this coordinate system, and observer A use this coordinate system to understand how observer B sees the world. For example, car is not moving on the dashboard, and the observer A apply physics to this coordinate, then get exactly what observer B see the world, okay, and vice versa. And we are including time in this, so it's possible that the car is moving, boy is standing, and boy said, wow, this car's clock is ticking slower than mine, okay, and this car look at the boy's clock and said, that boy has a slow clock, it's ticking slower. And that going to be possible because after conversion, the observer A may say T2, the clock, is slower than T1, right? And that's okay as long as applying a physics on this coordinate is consistent with the physics law, okay? That's what observer B sees. The interpretation before we divide the world, observer B's observation is explained only by translating to absolute space and time. But this time, observer B's interpretation, what they see, he see in his world, is exactly understood by coordinate transformations. The transforming coordinate into x2 and t2 and apply the physics law, the same physics law the A has, okay? So there's no such a thing that who is right. A may see B's clock is ticking slower, but B may see in the same way A is ticking, the clock is ticking slower. For example, A sees B moving with a glass of water, and B's observation is it's not moving because they are moving together at the speed v. And the A interpretation is, okay, I'm gonna use coordinate transformation to obtain x and t2, his coordinate and time, which is displayed on A's monitor. And A say, yeah, glass of water is not moving in front of him, and that's according to the physics law, that's correct, okay? Don't go back to Newton's word and said, oh, this one moving v and this one moving v, that's why. There's no comparison you can make. Only way you can do is the B's coordinate is available, and use this physics law to see how the world of B is. And that means you have to, world is divided into many places, okay? You are here, A, and B has a world, C has a world, and each world you do the coordinate translation and understand how the B see it, and the C, you need to understand how the C sees the world by coordinate obtaining x3 and t3. This is x2 and t2, and all coordinate obtained and your own coordinate follow the same physics law, okay? So how do we obtain t2 and x2? This is A, okay? A's monitor has a computer, and the computer does the work for you. Some kind of transformation equation used by computer to display the B's world, okay? And same thing happen for B's. The monitor shows A's world, and it's obtained as t1 and x1 using computer's calculation. So this conversion is called Lorentz transformation. And why not Einstein? Lorentz. Okay, this idea existed before Einstein, and great contribution by Einstein is the interpretation of what it means. Okay, the equation itself developed by Lorentz, and there is one more requirement. Every word see the light speed, the same speed. This is part of the physics law. We include that. So using this x3 t3 tx2 t2 or any coordinate you use, the light speed is the constant. Okay, so that's another requirement. And in order to make this transformation, the many the relative theory, special theory of relativity book show that, you know, the train's moving and light is shot and come back, make a triangle kind of things. That's not an essential part of the theory. It's just simply it helps to develop the transformation equation. It's using one example. Okay, and book use this kind of one example as if that's the basic theory. Is that confuse the student. The student need more broader view. This kind of story, you shoot the light to the moving train and the light come back, make a triangle and calculate the total time kind of things. It's okay. It's just one example. The basic things we need here is Lorentz transformation, and that's the like a Newton's laws equation. This is the basic equation for the special theory of relativity. And the theory of relativity uses a factor lambda. It's look like this, and this lambda is to make sure that certain speed c exists, that every observer see the constant speed, which is light. And that's, as I explained in the electromagnetic section, a lot of scientists confirm that the light speed seems to be constant by every observer. So moving observer doesn't matter, the light speed is constant. And this is a physical law. We have to incorporate this physical law into the transformation. So there is a lambda, and using this lambda, the car B in the monitor in the car A, which has a T2 X2, is calculated by this. And other way around, car A in car B's monitor, the car A is using T1 X1, and B can obtain the X1 T1 using this monitor, and the monitor use this equation to obtain T1 X1. Okay, so this is the transformation, and how we interpret this is the entire theory of the special theory of relativity. And how to interpret this is very confusing, because you are throwing away very fundamental assumption made by Newton. There is a single reference point in the space and time clicking at the same rate for everybody, and everybody can go back to the reference point and compare. We can't do that anymore because the world is divided, and A need to use this conversion equation to see how the B's world is, and A need to see use a conversion equation to see how the world C is, and every world uses the same physics law. Okay, and this is symmetric. B has the same situation as A, so physics law is consistent on every world. Okay, so this interpretation is pretty confusing, and initially it's kind of difficult, and that's why it's become an independent theory, and Einstein did a great job for that. But it's just interpretation of the world and the theory. It's no Nobel Prize granted for this. He just did the work and he became a little bit famous, but Einstein became really famous when he used the general theory of relativity and predicted something happen, physical phenomena, and it's happened, and that's made him very famous because New York Times and other medias reported prediction, and reported later the scientists confirmed. So whenever somebody make a very the special case prediction and it's happened, then his theory is right and become very famous. So one of the most important consequence of this equation is the time dilation. Time dilation is actually what I said. You converted and obtain x2 and t2 using that Lorentz transformation. Then t2 is always slower, ticking slower. The same thing happens is symmetric. For this guy, B, looking at A, and obtain T1. T1 is ticking slower than T2. And they don't contradict, because when you say T1 is T2 for someone and T1 T2 for somebody else, okay, it's two different observer. For example, say you're standing here and looking at this guy very far away, and you say, hey, you look very small, right? Then this guy say, no, you look very small. And who is right? Are they contradicting? They're not contradicting. It's the same thing. It's basically go back to the same thing. The glass of water on the dashboard. The car driver said, hey, this glass of water is not moving. But this guy said, no, come on. Your glass of water on dashboard is moving at speed v. Who is right? Well, both are right. In this case, both are right. You look small. The actual height, say, if 6 feet, this guy, and this guy is also 6 feet. But this view has the angle, and in front of him it's presented to be very small. It's a triangle formula. You can tell it looks small, right? So when he say, I'm 6 feet, this guy believe it? Sure, he see this guy is only 1 inch in front of him, but he use physics law and he get x2 coordinate from this guy, and look at the x2 coordinate and say, yeah, this guy is 6 feet. And that's how the physics works. The observer's saying is not necessarily correct number to use in the physics formula, right? So same way, glass of water on the dashboard. he said it's not moving, and he said, okay, let me obtain your coordinate system, x2 and t2. And yeah, you're right. I see how you look at the world. In your world, glass of water is not moving because the simple case is like, x2 equals 0. Right? But x1, the glass is moving at v t1. Glass of water is moving using his coordinate, but you look at his coordinate, glass of water is 0. It's sitting there and not moving. Okay, so he see the bee's world through the monitor. Okay, so is it real or just imagination? Well, actually, geostationary satellite is something that it's going around Earth at the same speed as Earth spins. So it's always on top of, say, here's an island. This one staying above the island. Okay, and it's moving at the v. So this guy, radius r, moving at v1, and this guy moving at the v2. There is a big difference, v1, v2. So this guy is moving against this guy. So what's happened is, this guy said, I check your clock. It seems like your clock is ticking a little slower than ours. We need to make adjustment. Okay. If men live in this geostationary satellite, he may say, yeah, your clock is going slower. Right? So, who is a user of this satellite? This guy. So this guy make a time adjustment. But you have to be careful in this example because this is a circular motion. Circular motion is not inertia because it has the acceleration. Then there is another effect, secondary effect. It's a general theory of relativity, and that changed the time. Okay, if you have certain acceleration all the time, then the clock speed change. So that also has to be adjusted. So to affect the clock, affect the clock on the satellite, and adjustment is made regularly. Your satellite is going around 3 years, some microsecond change happen, and microsecond is important because it's moving so fast. Okay, so that's example of time dilation. So what's happened if some event happen and A and B see it at a different time? Suppose he said, oops, water spilled, and he said, well, according to coordinate and T2 obtained from this guy, is A and B, I see water spilled. Then naturally you think, well, he thinks this guy's clock going slowly, and time its spill is, say, extreme. This guy's already 3 o'clock, and this guy is still 2 o'clock and water spilled. But from this guy's viewpoint, this guy is already 3 o'clock. And then, you know, this guy's clock going slow, so it's 2 o'clock. And water spilled when, in this case? Here, right? So, is this a contradiction? Again, simultaneity. The event happened at a different time. For A, it's happened at 2 o'clock of B's clock. For B, it happened 3 o'clock. So there's no longer simultaneity in the classic sense. Is it the problem? Not really, because physics law consistent for A, for the world A and world B observed by A, and the world is consistent for world B and B observing A. So there's no, B said, yeah, water spilled at 3 o'clock. That was 2 o'clock and A's clock. But A said, yeah, water spilled at 3 o'clock in my clock. But that was 2 o'clock in B's clock. And there's no conflict actually. They are living in 2 different worlds. So the event keep going with A and observed B. On the B's world, event keep going with B and observed A. So they don't conflict each other. Okay? This is something new, and a lot of people struggle with this. Some people thought simultaneity is a fundamental part of the physics. You know, something happened to you, happened to me, and happened to everybody at the same time. Otherwise, how can you make the physics law? Well, it's physics law is okay within your world. The physics law looks, you know, it's okay, exactly same, but the time actually looks different in the other world. Okay, so if simultaneity is gone, how about causality? Okay, the causality is never been violated. That's a conclusion. Causality is a basic part of physics. The event A causes event B. If event B happened before event A, then time flowing backward, and time flowing forward is part of the physics basic law. So causality is maintained. Some people say, well, you know, what's happened if the men leave the Earth, go to the space at high speed, and they come back? Then, since he can come back to the past, well, this is a wordplay, you know. The Hollywood used that trick. He come back to the past and meet a grandpa. It's called grandpa's fallacy. It's Hollywood love this, okay? And you kill the grandpa, so then you don't exist. So it's a contradiction. Actually, it's not. Say this is grandpa's world, right? And your parents' world. If they live together, they are living in the same time clock. This is T1 and T1. And you're born here, you, right? And you go space trip T2. Okay, so T2 is clicking slower. So when no, T1 is clicking slower. So when grandpa and parents become here, you are already here, right? And you go back to the earth, then you say, wow, my parents still young, it's only 1 year, I'm already 20 years old, and almost same age as my parents. You can never go back before you're born. There's no mechanism for that, because time ticking slower on the other world doesn't mean you can go back before the time you're born. So you cannot go back and meddle with grandpa's situation. You cannot kill grandpa. There's no way you can do that. And this is a theory proved that. Okay, so last subject in this video is maximum speed. Okay, so the special relativity, the special theory of relativity never say light speed is the limit. It's historically came as the example. Light speed was the example of setting this law, but theory itself saying there is a maximum speed you can go. And what is the maximum speed? Is about 300,000 kilometers per second. And what example of things going maximum speed? Light and a few other particles without the mass. So it's not about light. Okay, this theory simply said there is a maximum speed you can go, and this maximum speed observed because physics law is consistent, observed by every observer, same max speed exists. And the example is light speed. So the theory is not about the light speed. Theory is about max speed. There is a max speed that every observer have, and for the consistency of physics law. And that's what it is. And do not get confused, it's about light speed. The light speed is just one example, and there is other particle that goes at the same speed, c. So theory is about max speed, it's not light speed. Okay, I hope you enjoyed this video, and if you like, subscribe so you can move on to the next section of the special theory of relativity.